we have Kate Perkins, who's going to talk to us about the state of the basin, the state of the Scott River. This microphone. This is for Zoom. You can go ahead and put that on.
Oh, my voice all got changed. Okay. All right.
Slides here, advance to the back, and then just use the mouse for anything.
Okay, great. Okay. Hi, I'm Kate Perkins. My font all got changed a little bit, so hopefully the formatting is still okay, but I apologize if it looks a little funky. So yeah, I've been working, this is my first K-Bump in person, so good to see everybody. I've been attending online for the past few years. And I started working in the Klamath Basin in 2020 as I was wrapping up my master's degree at the University of Montana. I was introduced to the basin through Laurel Genzoli, who is presenting after me. And I have done work in both the upper and lower basins with Laurel, Jacob Kahn, as well as Eli Asarian, who I co-authored this report with. So I'll come back to this aerial image that we see. First, I'd like to go ahead and say thank you to the Klamath Tribal Water Quality Consortium. Yeah, see, I swear it said consortium at one point. It's just like the formatting is all off, so I apologize. The consortium funded this project as well as a lot of important work that happens in the basin and consists of the 5 tribes listed here, so thank you. And this presentation, the State of the Basin presentation, is available as a 2-page report that's going to be passed out, or I believe Eli just passed it out. It's also available online. It's a continuation of a previous State of the Basin report that was completed by Jake, Eli, and Laurel, and it was presented at the 2018 K-Bump by Eli and Laurel. So let's go ahead and get back into it. The Scott Valley in California, here's that image from the cover slide. The black line is the Scott subwatershed, and the blue line is the Scott River. You can see the mountains surrounding the basin that provide the snowmelt and the snowpack for it, and you can see the low gradient valley here in the center. And the Scott River is a large tributary of the Klamath. And like I said, the center of it has a very low gradient, and that means that it has high intrinsic potential as salmon habitat. Because of the low gradient of the valley, it also is a good agricultural and rangeland. Yeah.
Sorry for the interruption, everybody. Back to screen sharing.
Oh, that's very important.
Apologies for those out on Zoom.
Okay.
Thank you.
Great, thank you. Okay, is that going? Let me click it again just to make sure. Okay, there we go. Okay, so that means it is useful as agricultural and rangeland, and so there are extensive surface water and groundwater diversions, groundwater pumping to irrigate. And the Scott River is listed for 2 contaminants, temperature and sediment, and it is also impaired for other issues. However, those are the only 2 TMDLs in place. And this is the location of the Scott subwatershed relative to where we are here in Yreka, as well as to Northern California more broadly. Oops, is that working? There we go. And so great order for the talks. We just talked about salmon in the Scott River, so I'll also give a quick overview. So salmon populations are low in the Scott River as well as in the Klamath Basin more broadly. And salmon require specific conditions in the river to be successful. That includes in-stream flows, streamside shade from riparian vegetation, as well as access to cool water in the river. And when we have low flows, that can oh, I apologize. And high water temperatures can stress and kill salmon species. So low dissolved oxygen levels, it can hinder fish growth, alter migratory patterns. And so low flows in the river can actually cut off important habitat. And so in this image, this is from the California Fisheries blog. And this is a fall run Chinook salmon that cannot access spawning grounds in the Scott River due to low flows. Now, water quality impairments, many of them, of course, have several factors that contribute to the impairment. Today, we're going to discuss climate and human activity in the Scott Valley. So in terms of climate, and Randy, thank you for the great overview. So in terms of climate change and drought in the Scott Valley can decrease snowpack in those surrounding mountains, and that will reduce flows in the river, leaving the Scott River more vulnerable to warming. Climate change also increases air temperatures, and increased temperatures can increase water temperature in the river. And climate change increases the number of wildfires that we're seeing. And wildfires actually have the opposite effect, where the smoke from the fire can act like a cloud, shading the river and therefore cooling it instead of warming it. So for human activity, agricultural diversions that we talked about earlier, groundwater pumping, those reduce flows in the river, therefore leaving it more vulnerable to warming. And the removal or modification of streamside vegetation, vegetation in the riparian zone can reduce the amount of shade the river is receiving. And additionally, in the Scott Valley, historic mining practices have altered riparian vegetation, and this also leaves the river more vulnerable. And finally, CO2 and other greenhouse gases, aka climate change from human activity, warms the planet, therefore leaving the river more vulnerable. So for this project, our goal was really to broadly characterize the status of water in the Scott Valley, and to do that in a way that is concise and accessible to a broad audience in terms of the language that we're using and the figures that we're creating to create this report that we're passing around. We did that by characterizing 6 metrics. The first is water temperature. We sourced data from Quartz Valley, the Klamath National Forest, as well as the US BOR from the SRGA site located near Fort Jones. Oh darn, yeah. We sourced air temperature data from the Global Historical Climatology Network daily. And we used 3 different air temperature sites, which you see here. Our primary site was this CQUA here, which is the Quartz Hill. And for data that we're missing from that site, we infilled with data from the other 2 sites, as well as from PRISM data. We also got flow data from the USGS, the same flow data that were presented in the previous presentation. We used snowpack data for the basin, and this was from the University of Arizona. They calculated snowpack data from the California Department of Water Resources measurements. We used evaporative demand data, and this was calculated for the groundwater basin in the Scott. Evaporative demand is the amount of water consumed by irrigated grass if there is no cap on the amount of water available. So it's how much water the plants are consuming. And this was from the University of California, Merced, and it uses Scott Valley weather data. And finally, we also calculated streamside tree cover, and these were data from the University of California. They use satellite data to calculate different riparian vegetation covers, one of those being trees, and we calculated it for a 60-meter buffer around salmon-bearing streams in the Scott Valley. And there's more information, and so these are all of our sites together that we used. And to calculate decadal change, we used a simple linear regression. And there's more information about all of these sites, as well as how we calculated these numbers in a methods document that's available. Just contact Eli or myself. And so what we found So in this figure, it's a double axis, but it's presenting the same data. You have Celsius on the left axis and Fahrenheit on the right axis. This is water temperature. We have water temperature data dating back to the mid-90s. And the dashed line is our regression line. And so what we can see here are that maximum July water temperatures have increased by 0.88 degrees Celsius per decade, or 1.59 degrees Fahrenheit since the mid-90s. For air temperature data, once again, double axis with the same metrics on each side. The maximum July air temperatures increased by 0.61 degrees Celsius or 1.1 degrees Fahrenheit per decade. And finally, we have flow data from the 1940s, and the mean July river flow has decreased by 13.64 cubic feet per second per decade. Okay, yeah, no worries. Okay. Yeah, and so we ran all these data through QA, and so that's why you can see, for example, with the water temperature, we are missing some years, missing some data points, and it's because they didn't satisfy the QA process. But yeah, so we see that river flows are decreasing. Here, there we go. So the snowpack as of April 1st in the valley has decreased 7.04 millimeters per decade, or 0.28 inches per decade since the mid-80s. Evaporative demand, so the amount of water that plants need to be irrigated with in the growing season, April through September, has increased 6.95 millimeters per decade, or 0.27 inches. So the amount of water that plants are requiring to be irrigated for the same amount of growth is increasing. And finally, riparian tree cover around the Scott River has increased by 1.28% per decade. We can see some variability along the way, but overall has been increasing. And so in summary, we can conclude that climate change is increasing air temperatures, and this increases water temperatures in the Scott River. It leaves it more vulnerable to warming. And this is also increasing the amount of water that is required to grow crops. It's increasing the evaporative demand. Additionally, human activities in the Scott Valley have increased water temperatures. So we have a lot of agriculture and rangeland that is removing streamside vegetation and shade, as well as mining practices that have altered the streamside vegetation. And additionally, because of human activities, water flows, surface water and groundwater are being reduced due to irrigation diversions. And finally, the streamside vegetation cover in the Scott Valley is increasing. There have been remediation activities and cattle exclusion fencing. And so we do see an increase in the amount of vegetation. However, water temperatures in the Scott are still increasing. The restoration that we're seeing is not enough to offset the increasing temperatures in the river. So we're still seeing an increase in Scott River water temperatures. And so thanks for your attention. And once again, you can find the report here online, or it's being passed around today. You can also find the prior State of the Basin reports, as well as other studies that have been done at the website, or you can also, here's my website, you can contact myself or Eli for more information about this. And so with that, I will take any questions.
Great. Thanks, Kate. I'll start off with one. Do you have any plans to make these available for other subbasins in the Klamath?
I believe we have one planned for the Shasta subbasin. Is that correct? Yeah. Mm-hmm.
Cool.
Yes.
All right.
They will continue.
Great. Questions in the room? Yes, and let me get the microphone so people on Zoom can hear you.
Have you recorded a lot of like stream intermittency or refugia for species in the Scott River Basin?
That was a really great question. Great question. However, I don't know the answer to it because I'm not totally clear on detailed information like that. But Eli, if you maybe have an answer, or anybody else in the room who has information about refugia, cold water refugia in the Scott River. Yeah.
So definitely, like, there's some tributaries that are perennial that have cold water year round. Some of them dry up, some of them don't. And then the main stem does become intermittent in places, and places where it does become intermittent, those pools can stratify, and you can have cold water at the bottom of the pool, even though the top is hot and there's no water flowing into it. I don't know about any comprehensive efforts to try to sort of map that in time and space. I don't know if anyone else have any comments on that.
There has been some effort, and if you contact me, I can get that information for you.
There's some two infrared flights also. Yeah, through the helicopter base.
Yes.
Yeah, okay, thank you.
All right, other questions in the room? I think there's something online. What's the flow decrease total since 1940? That
I think it depends on how you model it, right? That will alter sort of this value for how the flow has decreased. I could calculate maybe like the number of decades and then the decadal change, but I don't have an actual value.
Okay.
But we can see, here it's like just over 200, and we dip below down there. But this is also mean July river flow. So I could calculate that and get back to this person.
Definitely a few ways to calculate it.
There's a
like
few
you
ways to
said.
calculate,
Yeah.
exactly, yeah.
And then one more question online. How does channel morphology impact temperature?
Oh, yeah, that's a really great question. I'm sure there's experts in the room that can address this, but from what I know of the Klamath, just doing snorkel surveys with Laurel and being out on the river, and this is for the Klamath. I know the Scott Valley has different morphology, but you do have like deeper places in the river, with the channel morphology, you end up with riffles and pools. The pools are deeper than the riffles, and so you can have cold water refugia in the pools. Like I said, I'm sure there are experts in here who have studied this exact thing. So,
okay. And then have you observed any relationship between functioning meadow and headwater areas and less of an increased temperature regime in connected habitats downstream?
that was outside of the scope of this study. So no, I personally have not found relationships and have not studied that.
Okay, thanks. Any other questions in the room? Yes. Eli.
Yeah, the other Eli. So with the Scott, it's a very, we'll just say like heterogeneous system, and using one point in the canyon far downstream is really a blunt tool, I think, to look at change in water temperature over time, especially when you think about the cold water tributaries. They do have a lot of refugia and do host the majority of rearing. Is there a future effort to expand this to include more data points and look at more of a comprehensive temperature picture of the Scott?
Yeah, I think that's a great question. That would be a really fascinating study. With this project, of course, you have to go with funding available. And with this project, we really wanted to use the resources that were already available to us. So we imported data that were already present. For example, water temperature data Eli had compiled for a previous project. And the rest of these data we were able to import from more publicly available sources. And so I think that would be a super interesting project to do. But in terms of, how we were able to operate with this study, this could be sort of a stepping stone for that, but we weren't able to get that detailed. But I'll make a note of it because it would be fascinating to learn that thing.
I have a lot. I already gave Eli a bunch of data, Scott, so there's a lot there. And then,
great.
Yeah, just keep expanding it. I think I want to look at the methods paper and see how it all worked out.
Okay. Great. Yeah, and I'm sure that you guys are already okay. Perfect. Yeah.
And I know with water temperature data, there's a wealth of water temperature data out there. Just when are you going to stop? Because I think there's, the last time we checked, like 600 different temperature probes that are deployed by all the different organizations out there in the basin. So
Wow.
take your pick.
Yeah. So,
so-
yeah, you're doing great work compiling this into one resource.
Yeah.
Yeah. Mhm.
So, great. Any other questions for Kate? All right. Well, thank you, Kate.
Great. Thank you, everyone.
right.